Dear friends, in this video we want to see together what is the physics behind the climbing, one of the most exciting sports. Actually, we do limit our study to only one aspect of the sport, that is the safety, and we want to see what happens when a climber falls, and what is the effect on the rope stress, its elongation and the deceleration of the climber's body. And we complete this study with some experiments. Let's start together. Hereby, the resume of the video's content. First, we clarify the matter of the study. Then we speak about the basic formulas and definitions. Soon after, we run the experiments. The first is for determination of the rope elastic property and is split in two parts. The second experiment is to see what happens when a body falls. Afterwards, we display the performance of the real climbing rope to understand what its parameters are meaning concerning the safety of the climber. Finally, we resume our findings and make some general considerations. Climbing is a dangerous sport because of the possibility to fall. The risk increases when lead climbing, the more the anchor points are distant. While climbing, we want to be safe. Therefore, we want following questions being answered. How can a fall stress the rope? What that stress depends upon? What is the effect of a fall to the climber's body? And to answer those questions, we need to make some assumptions. We consider only free falls without hitting rocks or ice walls. There is no friction between rope and carabiners. There is a linear behavior of the rope's elasticity, at least in a certain range. The rope elongation is negligible with respect to the free length. These assumptions allow using simplified formulas. The first definition, that is also the most important, is the fall factor F. It says the ratio between the fall height h and the length of the rope, capital L. It varies from 0 to 2. The higher is F, the more severe is the fall, as we will see soon after. Then we have the rope elongation, X max, that is the elongation when is applied the maximum force, capital F. This elongation depends upon the rope's length and the constant K0. K0 is actually a constant only if a linear elasticity of the rope is assumed. The impact force, capital F, is the force applied to the rope as a consequence of a fall. The formula displays that the force for a certain rope having elastic constant K0 and for a climber having mass m only depends upon the fall factor F. The stress is, for definition, the ratio between the above force and the cross-sectional resistance area of the rope, but from now on we speak only about force. We want to demonstrate now the impact force formula. From the conservation of the mechanical energy, we can say that the potential energy of the climber is equal to the elastic energy of the rope. The potential energy of the climber is mg times h plus x max. The elastic energy of the rope under linear behavior is 1/2 of k times x max square. The elastic constant k we can express as a constant k0 over the length of the rope. By replacing the elongation x max with the force capital F as defined in the previous slide and neglecting x max with respect to the fall height, we come to the expression of the force under the square root on the left side. By replacing the definition of fall factor F, we get the expression on the right side already seen before. Important to notice that for a specific rope and for a specific climber, the force depends only upon the fall factor F, and the more is the fall height for a constant F, the more is the elongation, as you can see from this expression, where the elongation is really proportional to the fall height h. Now we want to introduce a couple of experiments. The number one is repeated twice, and we do to assess the elastic constant K0 of the rope. We do once with the length L1 and the second time with the length L2. Then the second experiment is to meter the dynamic behavior of the rope. Let's see first a small introduction.
We are now with a rope, with a sack, and we want to meter how the rope elongates because of the loads. And we will try the experiment in two steps. First step, we leave this sack hanging with different weights, and we assess the elongation of the rope and the load by means of the dynamometer and by means of a tape meter. Second experiment, we will try to leave the sack fall from a certain height, and we assess if the elongation of the rope increases because of the fall.
The first experiment is adopting a rope length of 155 centimeters, and they are applied three different loads, 8, 15 and 22 kg force respectively. For the trial has been used a sack filled with bricks. Here is the sack and here are the bricks. Between the sack and the rope is placed a dynamometer, and hereby are the results. The elongation and the loads are building a chart. The regression function shows that the slope is 3.72 kg force per centimeter, and to find the constant K0 we need to multiply this value for the length of the rope. The corresponding value in Newton is 5641. The second part of the experiment uses a longer rope, this time 580 centimeters, and because of the length we had to use a pulley in between. The applied loads are always the same. Here are the results. The regression line now shows a smaller value. This value we have to multiply for the new rope's length to obtain the K0 value. This time K0 equals 6543 Newton. We take the average of the found two K0 values. We get 6092 Newton. We want now to compare this value with the elastic property declared by the manufacturer for the same rope. Under the specification, we find the static elongation, 7.7%. This is conventionally the elongation when a load of 80 kg force is applied. If we divide the load for the elongation and convert this value into Newton, we find K0 equals 10,192 Newton. That is significantly higher than our value. The result is realistic, since the behavior of the climbing rope is not linear. The rope becomes stiffer the greater is the load. Now the second and last experiment. We need to simulate a fall. For that we use a water canister of 5 liters instead of the sack, since it is more resistant. The fall height is 1.7 meters and the rope is now 6.7 meters long. The theoretical impact force we can calculate by replacing the values in the formula. It says 404 Newton. The corresponding maximum deceleration is then 7.1 times g. G is the gravity constant of the Earth, and the rope elongates of 44 centimeters. If we consider only the dynamic part of the elongation, also subtracting the static one, we come to 39 centimeters. In the video, we will see, with a slow motion, that the canister has a dynamic elongation of about 33 centimeters. This value is lower than the theoretical one because of the friction losses. Let's see now what is the performance of a real rope in terms of impact force. From the specification, we read that the dynamic elongation is 37%. This elongation corresponds to a low impact force of 7.4 kN. The meaning of low is that this force the rope can stand without losing its performance. Actually, it is possible to go something over 7.4, but the rope life will be affected. The constant K0 we find by dividing the force F for the elongation. We get 20,000 Newton. Question is, what fall factor the rope can stand for a climber with a mass of 80 kg? The answer gives us the impact force formula solved for F, that is 1.74, also less than 2. The deceleration under such condition is 8.4 g, also very high. Now some final considerations. The elastic behavior of a rope is actually not linear. K0 is not a constant, but increases when the force increases. The impact force of a rope depends upon the fall factor only for a given climber mass. For a certain fall height and climber mass, the maximum elongation depends only upon the rope's length. The higher is the impact force, the higher is the maximum deceleration. High deceleration, greater than 7g, is also affecting the health of the climber. The friction of the rope to the anchor points, especially the carabiners, can change significantly its elongation. It gets reduced because the rope will be stiffer, and the impact force that can be increased or reduced, so that the above calculations must be taken only as reference. To increase the safety of the climber, it is recommended, strongly recommended, to keep the fall factor as low as possible. Thank you for your attendance. See you next time.